Hi everybody, my name's John Mills. I work for Pancho Training Consultancy, and what we thought we'd do is put together a short introduction to IP addressing based around the CCNA course. So without further ado, let's get stuck in. Okay, and an IP address is a 32-bit number, 32 bits long. It looks like this. As you can see, it's just a series of zeros and ones. And a computer or a PC or a router would have absolutely no problem at all reading that IP address. Our problem as human beings is that we don't work in binary, and therefore we can't talk about that binary number with any ease. If you can imagine it, if I say, what's your IP address, and you said, oh, it's a 00001010000, it's very, very easy to forget a number like that. So the first thing we have to do in order to be able to talk about IP addresses is represent them in some format that we can understand. So what we're going to do is we're going to take that 32-bit number and we're going to cut it up into 4 8-bit chunks. So it looks a bit like that. So instead of just having one great long 32-bit number, we've now got 4 8-bit numbers. And then what we're going to do is we're going to represent each one of those 8-bit chunks with a decimal number. Now it's much easier to convert an 8-bit number into decimal than it is a 32-bit number. So let's see how we do that. Okay, there's the first 8-bit chunk. As you can see, it's 4 zeros followed by 1010. And if we put our little conversion chart down there, ranging from 1 to 128 with different bit positions, you can see that we've got a 1 in the 8-bit position and we've got a 1 in the 2-bit position. And if we add the two together, 8 plus 2, we get 10 decimal. Okay, that seems to be working. Let's try the second octet. There's the second octet, the second 8-bit chunk. As you can see, we've got 3 ones set on this one in the last 3 bits. So if we convert that back into decimal using our same chart, you can see that we've got a 1 in the 4-bit position, a 1 in the 2-bit position, and a 1 in the 1-bit position. If we add those 3 together, we get out 7 decimal. Okay, let's just do the same thing with the last 2 octets. So there's the third octet. As you can see, we've just got a 1 in the 4-bit position and a 1 in the 1-bit position. If we convert that into decimal, we get out the decimal number 5. And finally, the last octet, just got a 1 in the last bit position. That equates to a single 1, so we've got a 1 decimal when we convert that back. Okay, so let's put the whole thing together. And what we get are 4 decimal numbers, 10, 7, 5, and 1. And just to separate them so that we can understand each one relates to a specific octet, we're going to put a dot between them. And that's what's known as dotted decimal notation. So our IP address at the end of the day can be described as 10.7.5.1. Now the important thing to understand here is that's just a decimal representation of a real IP address. A real IP address is 32 ones and noughts. It's just a decimal representation. You can't do any maths with it, but it allows us to talk about it a bit easier than it is in talking in binary. Okay, now all network layer protocols, all protocols used by computers at the network layer, are split into 2 parts. We have a network portion of the address that describes the piece of wire, and we have a host portion of the address, or node portion of the address, and that describes the host or device on that piece of wire. So let's have a look at one here. We've got Novell IPX, that's Novell's network layer protocol. That's 32 bits of network addressing and 48 bits of host addressing. Always fixed line, 32 bits network, 48 bits host. What about another one? Here's AppleTalk. AppleTalk, 16 bits network, 8 bits host. Always 16 bits represents the wire, 8 bits represents the host on that wire. One more, DECnet, an old protocol I know, but I guess it's still around somewhere. 6 bits network, 6 bits represent the wire, only 10 bits represent the host. They are all fixed lines, so it's always 6 bits network, 10 bits host. Let's look at IP then. The problem we have with IP is that there is no fixed line. The network host portion of the address moves, and it moves depending on how we're using it. So we can have lots and lots of networks with only a few hosts, or we can have lots and lots of hosts with only a few networks. So we could split it like that, and the original implementation of IP was split just like that. The first 8 bits were network, and the last 24 bits a host. That gives us somewhere in the region of potentially 256 networks. Each one of those bits of wire can support up to 16.7 million hosts. Or we could draw the line right in the middle there. So we've got 16 bits of network. Half the address represents the wire, and half the address represents the host. And that would give us something like 65,000 networks, each one of which could support 65,000 hosts. Or we could take the network portion right down to the right-hand side here, and you can see that we could have 24 bits of networking with only 8 bits of host, and that will give us something like 16.7 million networks, each one of which only supports 8 hosts. Okay, so back in the early days, way back, somebody decided that that's how we split them up. And what we do is create different classes of address. And the first class we're going to choose or create is something called a Class A network. And the Class A network consists of 8 bits of networking space with 24 bits of hosts. And that gives us potentially 256 networks, each one of which can support 16.7 million hosts. So we'll give these to the big companies, the huge companies, the IBMs of this world, the Hewlett-Packards, the US government. They'll all get a Class A address. For medium-sized companies, we'll give them what we'll call a Class B address. Class B address consists of 16 bits of networking space with 16 bits of host space. That means we've got 65,000 odd of these Class B networks, each one of which can support up to 65,000 hosts. Okay, how about small companies? They get a Class C address, and the Class C address is essentially 24 bits of the address represents the network, and only 8 bits represents the host. So you've got lots and lots of networks, 16.7 million networks, but only 8 bits of host space. So you could have potentially 0 to 255, 256 hosts. We're also going to create another one. We're going to call it a Class D, and we're going to keep that for something called multicast addressing. Multicasts are when you have a single source, single device transmitting to a group of hosts. So things, if you think of something like video conferencing, where you have a single video server sending traffic to a group of devices that are listening on that particular video channel. And we're going to create one more class of address called a Class E, which we're going to reserve for ourselves, something we can play with later on. Okay, that's great then. So we've got 5 different classes of addresses. Problem is, how do we tell the computer that these addresses are the ones that we want to use, and that each address, after all, it's just a 32-bit number, is either a Class A, Class B, or Class C address, or come to that, Class D or Class C. And we're going to have a look at that, how we do that, in the next portion of this little course we're running. So that's the end of part 1. Hope you've enjoyed it so far. Don't forget to look out for part 2. Part 2 will be somewhere close to where you found part 1. Thanks a lot. Bye.